Today I'll focus on the high-frequency QPOs in accreting black hole systems for reasons you'll see as we go on. Basically, they may provide the most fundamental information. And one way to test our theories of QPOs in black hole systems is by comparing their predictions of angular momentum of the black hole with that from these other two methods, which I'm sure you're familiar with, and John just talked about one. So I'll just go briefly through that. Okay, what I call a continuum method just uses a Stefan-Boltzmann equation, and a distance is required to get the radius. Whoops, I see what you mean, Roger. Yeah. So you get what? Let me use a keyboard. Yeah. I think there's a time delay here. Okay, so the first use of Stefan-Boltzmann method, knowing the distance, you get the radius. Same idea, except you have to know the inclination angle as well if you're dealing with an accretion disk. Okay, and knowing the radius of the ISCO and knowing the mass, which is one of the hard parts, you get the spin. Okay, let's see if it works now. Nope. Okay, this is the other method I call the line method that John calls, and many people call it the reflection method. Okay. There you just look, you see the large gravitational redshift, mainly gravitational redshift from the spinning black hole. Okay. And so the larger the redshift, the closer the disk is to the black hole, and therefore the greater spin of the black hole. And I'll be talking about the measurements in detail in a minute, hopefully. Should I use this thing? Okay. Now here are the observations as summarized by Ron Remillard as of a year or two ago. Not much has changed. You see there's 8 black hole binaries with high-frequency QPOs seen in our galaxy. 4 of them have more than 2 frequencies. And these frequencies are stable, okay? Not unrelated to the fact that you're probing the strong field of the curved black hole. I believe it's a gravitational cavity, not a gaseous or magnetospheric cavity. And in these 4 systems, the 2 highest QPOs are in a ratio of 3 to 2. Okay? What I consider a fundamental mystery, analogous to atomic physics 100 years ago, if we believe Ron Remillard and others that these frequencies are real. In 4 other systems, you see a single frequency. We'll talk about SIG-X1 a little later as well. We'll skip this. We've calculated normal modes of fully relativistic accretion disks since the 90s. Okay, here's the key physics. We're plotting the 3 key frequencies: orbital, vertical epicyclic, and radial epicyclic versus black hole spin. Okay. Reminding you where the event horizon is as you spin up the hole. And the basic mode we'll see, the fundamental G mode, which is the most visible and the most robust mode, is trapped below the maximum of the radial epicyclic frequency, okay? The frequency that precesses Mercury's orbit. Wow. Why is mine taking so long? Should I use this? Should I use this thing here? Yeah, but okay, so I know it'll come. Now here's where the G mode is trapped, right out here, where the disk is hottest, and there's no leakage into the black hole as there is for the P or acoustic modes and the corrugation modes. One trapping radius is the inner edge of the disk. So I consider this more robust, more visible, more radius, modulating the X-rays. So it's the axisymmetric G mode we're interested in. That doesn't, oh, good, I'll use that. Okay, just to remind you, here's the frequency of that mode versus black hole spin. You'll see this again. I just want to mention here that we have introduced weak viscosity into our hydrodynamic calculations and find that most modes, including the G modes, grow at a rate of order alpha omega. Okay, so we want to test, first goal is to test discoseismology, and in some ways I'd like to rule it out so I can stop worrying about it. So can we rule it out? Yes. Okay. Well, I believe the frequency stability, as I said, means you have a fixed cavity, which means gravitational trapping, although you'll see an exception in a minute, thanks to John McKinney and Roger Blandford and Sasha here. As I said, the fundamental G mode should be the most robust. I won't go into this detail. Okay. The basic mystery is here. What is the other mode in the 3 to 2 pairs? We believe the G mode is the 2. What is the 3? Okay. I don't believe anybody has a good idea for this. Okay. So there's various, I'll show a simulation in a minute. Okay. We're studying the effects of magnetic fields on the mode trapping, first studied by Fu and Lai. Okay. And they indicate a vertical magnetic field may untrap the modes if it's large enough. But it's, from our recent work, it's no longer clear. Wow. So here's what Reynolds and Miller found in 2007 in the pure hydro and hydroviscous case. You show the power and pressure fluctuations. Blue is the maximum power. Here's the radial epicyclic frequency. Here's the G mode trapped below that. This spacing is due to the speed of sound. It agrees with their calculations. It's just two different resolutions. So it has been seen in hydro, but not in MHD. Okay, we'll come to that later. How am I doing here? Okay, here's something new, as I said, from John, Sasha, and Roger, okay, which was discussed yesterday. A nice talk. So you saw this simulation. Of magnetically choked flows. What they find is a QPO, an M equal 1 QPO, driven by Rayleigh-Taylor and Kelvin-Helmholtz instability at the interface between the low-density jet and the high-density disk in this region. M equal 1, okay, at roughly this frequency, okay, within 10% roughly of that frequency. How am I doing? 2? Good. Okay, so that's the news. Okay. Okay, this is what I want to focus on. Let's look at the highest frequency QPO seen in these three sources. Okay, these are the three sources that have good masses, so we can calculate this key quantity. The observed frequency for 10 solar mass, properly scaled, for these three sources, 1915, 1550, and 1655. Due to the line method and continuum methods. I don't know if you can see the difference between the symbols, but I'll go through this briefly. 1915, we have concordance between these two, line and continuum, but this one is off, but it's an older one. Okay. Here we have 2 lines and 1 continuum measurement, and again 2 lines and 1 continuum measurement for 1615. Okay. This is the highest frequency QPO. Here's the prediction of that magnetically choked accretion flow. Here's our G mode. The width is due to the speed of sound, which depends on the luminosity, which we've taken to be in this range. Gives you this width for the frequency distribution. Okay. So for the highest frequency, QPOs. Okay? I let you draw your own conclusion, but the G mode, and this one is typically below these guys. But I want you to remember one thing from this slide. Here's the ISCO. Many, many QPO models, okay, have frequencies close to the ISCO frequency. Okay? And remember, this is the highest frequency QPO. Okay? The ISCO frequency is well above these frequencies here. Well above. In my opinion, this rules out all models of QPOs whose frequency is close to the ISCO. Here's the second highest frequency. Here we get better agreement, both with our G mode and with the magnetically choked flows, although there's significant discrepancies, but there's discrepancies in the spin measurements as well. So time will tell what's going on here, but we're not grossly inconsistent with the spin measurements from these other methods. Okay, so this is the main takeaway slide. Okay. And of course, the ISCO is even less able to explain this. So all ISCO models are out. Okay, I want to talk about SIG-X1 for a minute now, which was mentioned. Okay, most of the recent measurements indicate a high spin. We get a high spin also. There's only one QPO here. Okay, so let's try to go back. See if we can go backwards here too. Come on. Okay, so SIG-X1 with one QPO sits right here, high spin, 200 plus or minus 14, high spin for SIG-X1, okay, which agrees with our G mode. Okay? And you see the magnetically choked stuff rises much faster than the G mode because we do not approach the horizon as A goes to 1, okay, basically. So there's a big difference at high spins, small difference at low spins. Okay, I'm coming to the summary. I'll get there eventually. I know it. Okay, so here's the conclusions. I won't read this. It's what I said. Consistent in some cases, apparently inconsistent in other cases, but so are the other determinations. So a lot more has to be done. I mentioned this. ISCO models are out. Some QPOs may be coupled to the angular velocity of the black hole, as indicated. The main message is we need better determined masses in some cases and spin in other cases for the other sources with QPOs. And hopefully there'll be other satellites in the future that'll get us more QPOs, like LOFT. Thanks.
Well, you discussed the clock. Could you...
discuss what?
You discussed the clock in the QPOs. Could you say a little bit more what your current thinking is as to how that gets transmitted into sort of like 10% modulation of the hard X-ray emission?
Yes. Our view still is that because, as far as I know, in every energy spectrum, okay, taken at the same time as a QPO, there is some thermal component to the energy spectrum. So we believe the modulated photons leave the inner disk, are Compton upscattered, and as we calculated, that gives a very steep energy spectrum from the Compton upscattering at optical depth of order 1. Okay? And so that's how we believe you can match the energy dependence of the QPOs, if that's what you're asking.
You can get high enough modulation, you think?
We think, yes, as long as the optical depth is 1 or less. It won't be demodulated from our calculations. I can't see how the corona could produce a stable frequency, frankly. Okay?
Anatoly?
What's the big difference between an accreting black hole and accreting unmagnetized neutron star as far as
Okay. I've always assumed there's a small magnetosphere, okay, between the accretion disk and the neutron star because as you increase the mass accretion rate, the QPO frequency goes up, which is just what you expect from a compressed magnetosphere. Okay? In all cases that I know for neutron stars. So,
LMXBs have very weak magnetic fields.
I know, but it looks like it's still getting compressed because as the mass accretion rate increases, your QPO frequency goes up. Same thing for white dwarfs, by the way.